Awesome. Well, thank you everyone for coming. This will be our final journal meeting of the quarter, and this will be a really good time for us to kind of take a look at everyone else's projects and see what everyone else was able to get done. And yeah, if any of you have any questions, please, if you have questions for a specific project, we'll we'll hold some time after each team lead is able to present if you have any questions, and if not, you can hold it to the end as well. But I guess without further ado, let's go ahead and get on to the first project. There we go. The pain evaluation project.
All right, so this quarter we chose our design concept. We will be moving forward with an app that will be used to collect data on the way people report pain. There are a lot of apps already that help with chronic pain tracking. So this will be focused more on what if a patient comes in to the doctor's office with some kind of acute pain, and what does their number mean when they answer on a scale of 1 to 10, because while a more in-depth scale would be more helpful, doctors usually don't have time for that. So it would create like a population baseline that could be compared to and an individual baseline that could be compared to. So it would have a sliding scale of, well, this patient usually means this when they say like a 6 based on their previous data and based on the population's data with regard to this specific event. This is where people usually rate their pain. So we have started wireframing this app and trying to figure out what it should look like in terms of user interface, working out some of the design requirements that would go into that, like security, HIPAA requirements, because it would require identifying the information and it would likely connect to the electronic health records to make it useful to doctors. This would mean that it would have to follow HIPAA regulations. So security, privacy, how would data be stored, that kind of stuff is what we're kind of working on right now. Our main challenges have been hearing back from people and getting in contact with people. We've been working on a survey, which was supposed to be put out in early last month. And it hasn't been because IRB is apparently moving very slowly. For those of you who don't know, IRB is the internal review board that lets you know whether or not you can continue with a survey or some sort of research on humans or animals. And we had difficulties determining what direction we wanted to take in terms of a design because of how complicated pain is, because it has such a psychological component to it. It can't just be fixed with a product, really. It has to take into account the variability and subjectivity that goes along with interpreting pain. And kind of going back to hearing back from people, app development expertise. All of my members are BMEDs at the moment. So we are currently working with Dr. Hawkins and potentially a master's student to find that expertise and hopefully get a user interface that is not functional, but would help present our concept as we move forward and kind of demonstrate what we're trying to make happen. And if this project were to continue next year, we would recruit more CS students. Kai, say if you can go to the next slide. So this is just it's blurry because of the way I screenshotted this. You can't see any details, but this is kind of what it looks like. It moves from signing in to logging in to the home page and then to the user input, the access to the data output, account settings, and I believe the last one has to do with our website and like mission statement, privacy policy, etc. And then the next slide is a slightly more in-depth look at the user input side of things. And we're currently using the GIL index to start setting up the skeleton of that user input, especially with regards to pain, because that is a much more in-depth survey that is often actually used in, I believe, physiotherapy settings. So that's our project so far.
Awesome. Any questions for that project? Awesome. Right. And we have a slide out of place. But next we have the seizure prediction device. And I'll go ahead and let Ellie and Drew talk about that.
Hello. So this quarter, we were able to get Arduinos and sensors for our project. And we have those out to pretty much everyone in our group now. We've been working on collecting baseline data from the different sensors to kind of compare. So we have two different types of heart rate sensors and one GSR sensor. And we're trying to compare just like baseline data to see what is which sensor is more accurate and what sort of sensor we would want to use to try to predict seizures. So far, the heart rate data seems more promising than the GSR sensor data that we've seen, but we haven't decided between the two heart rate sensors that we have yet. We have some more stuff that we want to try in the future. And then in terms of actually predicting seizures with that data, we've been researching different types of software to do that. Obviously, there's just hand coding some sort of algorithm to do it. But honestly, I think it will probably take something more complicated than that. I think neural network learning could be really helpful and promising. That's a problem for us though, because we don't have any CS support right now. So I think going forward, if that looks like something we want, we'll need to do some recruiting on that front. Can you switch slides? So this is an example of some of the data we've gotten from each of the two heart rate sensors. So one of the sensors we're using is the AD8232. And something that's really important is the lead placement. You can see that I think the top signal has a heart rate in there. I would guess if you filtered that, you'd find one, but its data is so noisy that you can't really tell. But with good sensor placement, the heart rate is clearly visible. And this sensor in particular has the option to add more leads to it. So Ellie can talk about that later, but we're going to test that. And then on the right, Troy, one of the members in our group, took the sensor data actually from the 8232 as well, and he put it into MATLAB and used a Fourier transform and then a filter on it. And you can see it improves some of that high frequency noise and got a cleaner signal out.
Okay, so our goals for spring quarter are we're gonna continue working with 3 different sensors we have and identify which one we think is, I guess, superior, which one we think we can help move forward with to get the most successful data. And so we started collecting, as Drew talked about, data during baseline data just during resting. So our next step would be to collect data during strenuous activity. And we're hoping to write code to recognize like an abrupt change in heart rate. Right now, we'd be working on that between baseline and like a strenuous resting and strenuous activity. Whereas in reality, we hope to alter that to be able to identify a change in heart rate coming on with a seizure. And as Drew was also talking about, we currently have in one of the sensors, we're using it as a single lead ECG. And so we want to alter the hardware to change it to a 3-lead ECG. And we're anticipating that'll get more successful and more detailed data. And then right now we're using Arduino for computing, but we want to look into using Raspberry Pi or custom to work with different softwares. And then lastly, because we do want this to be a wearable device, soon we want to begin the ergonomic design of how this is going to fit onto the body, where the person is going to wear this, and everything like that. So does anyone have any questions?
If anyone has any, I think the idea of using the Raspberry Pi is super interesting because I know you can do a lot with those. Like there's a ton of different configurations you can use with Raspberry Pi, so that'd be really interesting to see. Yeah. If there are no other questions, we can go right on ahead to our next project. The gluten sensor project. And unfortunately, Tomvi is unable to come to the meeting today, but Ali will be able to present on her behalf today. So.
Okay, cool, thanks. So basically for the gluten sensor project, this quarter, they kind of identified what testing approach they want to take. So basically how the gluten sensor is gonna actually sense the gluten. And then from there, they began working on how to actually like test their design, and any of like the mechanical design concepts that they're gonna have to integrate into it. And they also reached out to faculty members to kind of get advice on the more specialized areas of the project. Oh, can you go to the next slide? Sorry. And so here's a breakdown of the testing approach. I won't read through every single thing. We'll post this online later so you can look at it. But essentially, it's an electrochemical aptamer-based competitive assay, which uses magnetic beads to help make the test a lot more efficient, and also smaller in size so it can fit into a portable device. And yeah, basically the device sort of breaks down the food to allow it to sense the gluten, and then the magnetic beads kind of help create more surface area for it to actually bind to the gluten. And here's a few design concepts. Basically, it's like a multi-chambered device where each chamber kind of serves a different function in the assay. And then also these will be like disposable cartridges, basically. And there's a sort of like snapping mechanism that'll kind of like combine each compartment at each point of the test and allow it to kind of move through those steps that were on a previous slide and actually process the food sample. And here's kind of a more detailed description of how that snapping mechanism actually works, and how they're actually kind of like filtering the food sample. They're going to have like a rod that sort of crushes down the food, and also kind of like breaks through some of the seals in the product. And then it also kind of shows like a food chamber and a buffer chamber. It kind of demonstrates like how the sample is going to be like moving through different solutions and stuff to kind of process it. And then they also have alternatives to test to the snap mechanism that help act to separate those chambers, and again just kind of facilitate the testing process within like one singular container.
Yeah, I would ask if there's any questions, but unfortunately, Tommy isn't here to be able to answer.
I think there's one more slide.
Oh, I think it may have gone in on
Oh wait.
order.
Oh, never mind. Okay.
There is a slide with challenges. It's just up ahead.
Okay.
You want me to go to it?
Sure.
Is it?
Okay. And then sorry, our PowerPoint got a little like jumbled up, but basically the challenges for next quarter are going to be integrating the electrode into the test. This actually creates the signal that tells you like how much gluten is in the sample. making sure that the measurements they're getting are pretty precise, and then like simplifying the design of the product if they can. And yeah, just coming up with like all the testing protocols to be able to see if the product actually works. Yeah. Okay. You can go back to the next slide now.
Yeah, this would be a really cool project to see, kind of have the opportunity to get in-person testing and kind of further work. So, we're definitely hopeful next year that a lot of our projects will be able to kind of take advantage of any possible in-person access to further their projects. And next up, we have the Electrolyte Monitor, and we'll have Ali speaking on that one.
Okay. So this is the project that I'm actually working on. And what we've done this quarter is actually create a 3D model for a wristband prototype and also write a sort of 3D printing combined with a molding process to be able to actually create like a flexible wristband, which has space for electrodes in it. Will help us eventually move on to benchtop testing and kind of see whether the device works with electrodes placed how they would be in sort of like a small wearable device. And then in terms of, we're working kind of on computational modeling of how the electrodes interact with the skin, and then also working on circuit design and prototyping based off of a research paper that basically did a lot of the groundwork for us and created a setup for a low-cost version of an iontophoresis device with circuit elements that are available like pretty easily online. So what we've done now is start to model this setup that they created in Tinkercad, and then also ordered parts to be able to hopefully by the end of this quarter or next quarter actually put the circuit together. And then from there, we'll have to figure out how we actually test whether our circuit is working. And then as far as the computational modeling is going, we're still just trying to figure out how to make it work and how to model the behavior of ions and electrolytes in the skin as they react to the electrodes to see if once we apply this iontophoresis to the process to the skin, and we know that it's putting out the right amount of current, that current is also producing the desired response from the body. So yeah. And then I think who's leading sort of the microfabrication part is here to speak a little bit about that.
Hi, can you guys hear me?
Yeah.
All right. So for the microfabrication section of this project, I will be fabricating and designing an ion-sensitive field effect transmitter device, and that will allow us to receive an electrical signal based on the electrolyte concentration in a solution. For this quarter, we've been mainly working on a simulation and characterization of the dopant diffusion that takes place in the microfabrication because we do not have access to ion implantation there. This dopant diffusion simulation is working currently, but it's rather basic. We're currently working on adding modules to differentiate different layers so that there's diffusion between the silicon and silicon dioxide layer instead of just air and silicon or a vacuum silicon. And then just some changes to the simulation variation and changing it from a time step, from a distance step to a time step instead. And currently we are working on in-person dopant diffusion characterization, but there are a few issues with that. So that will be delayed. Can you go to the next slide, please? These are results from the dopant diffusion simulation. I think they look good in terms of results that I've gotten. They're accurate as of now, so I could at least say that there's some progress in that. And next slide, please. And currently, in terms of the fabrication process, we've started designing the photolithography section of the fabrication. Hopefully, we will be able to finalize some decisions in photolithography by the end of this quarter, if we have enough time in the microfab to see and decide on what supplies are available. And hopefully during spring break, the rest of the fabrication process will begin getting fleshed out. That's it. Thank you.
Awesome. Are there any questions for Ali and Wee? This seems very, very interesting. Very, very much out of my scope. All right. Awesome. So now I'll get a chance to talk with Kajal about the Epipen redesign project. And so one of the things we were able to do this quarter is we were able to decide on our optimal design configuration. This is something we've been kind of bouncing back and forth on, but after working as a team and kind of bouncing our ideas off of each other, we were able to come up with an idea. And we were able to take this optimal design and make a Solidworks model of it. And we'll be able to show that off in just a bit. And we've actually even been able to move into 3D printing these parts. Obviously, the facilities on campus are not accessible. However, thankfully, feels like more and more people these days have a 3D printer, so that's definitely been helpful for us. And another bright spot for this project was being able to find these pico-cylinder gas cartridges. These are a relatively new product, and actually before, when I was working on this project, they weren't available. They're, I believe within a year of releasing, and they're FDA approved, or they're FDA cleared, and they're basically made for this type of configuration of using an auto injector. So, and yeah, and it was great because there's a Cal Poly alumni working there who was able to help us out. So definitely stay connected with the alumni. They're very great people. But looking at the napkin sketches, here's some of the early designs that we had. What we like to do is use these gas cylinders as the main energy source for injection. And we're going to use this gas cylinder to press on the syringe of the vial in order to press the epinephrine out. And I guess a bit of background is we're not intending to use a needle as is conventional. We're trying to use needleless injection, where we create jet flow of the fluid, and that'll actually be able to pierce the skin and deliver the drug and actually get a more even dispersion. So it has no negative drawbacks compared to the needle. It provides, ease of mind from the use of a needle and any dangers that can come up with needles. But on the left is one of my early sketches, trying to kind of dimension out this part and have it fit within our portable design requirements. And you can see in the middle on the right, those are a bit more fleshed out sketches where we're toying around with how to have this cartridge punctured, what mechanism to use to ensure that it was puncturing it with the same force every time, and also that it couldn't be punctured without the proper steps of the device being used. And moving forward, here's our initial SolidWorks model. You can see on the left, it's very wide, and our goal with this one was to have the mechanism kind of centralized, and it would be the CO2 would actually flow through and around it. However, we found that this would cause our device to be a bit too long, because we would have to stack on this cartridge, this mechanism inside the vial to actually contain the epinephrine and the volume that it will take up, and then also the proper distance for the depressing tip. So we found it to be a very long iteration. And so as Kajal will talk about in just a moment, we decided to move on towards a kind of a stacked design where many of our components can actually fit within each other, allowing them to kind of condense themselves, and also it allows us to reduce the amount of moving parts by keeping parts of the device fixed to each other. And here we have our current iterations.
So, sorry. So as Kesai was saying, you can see the difference between the last model and this new model, where we were able to save some of that distance and shorten the actual width of the model by putting parts on top of each other and really optimizing the idea of making this like a wearable keychain type device that is portable and smaller than the size of the current EpiPen, which is something that a lot of people with EpiPens currently complain about. So here is one iteration that has just kind of these ends to the model kind of free, and then on the right you can see we've kind of closed off those ends, and we're toying with both ideas right now, seeing which one is best for the actual design of the device. And now I'm going to go into explaining a little bit how the actual mechanism works. So it starts off by the blue part essentially being this type of depressing tip that is able to push into your skin. And you can see like on the right here that we have like a picture of like what the thigh, how the thigh would interact with the actual device. So you're going to start off by pushing this blue tip in, and you see in the second picture, the orange part pushes up into this purple part, which is connected to the needle, that makes a very close contact with the cartridge, but doesn't actually touch it. What happens next is the balls that are here on this picture on the left actually fall into the red part, and the green little ejector that is connected to the spring pushes up and actually takes the entire mechanism and with a lot of force jets it into this cartridge that is connected to this hollow needle. And then that hollow needle is going to actually have enough force to puncture the CO2 cartridge and inject down into the valve where the actual CO2 and the epinephrine will be, and it will eject into the skin at enough force to make a clean and safe ejection into the patient. And we just wanted to show off a little bit of our 3D printing as well. These are 2 at-home 3D printers that our members have acquired, and it's been a really, really great process being able to build the 3D printer and work with the actual the different materials. We're playing with PBA or PLA to see what the best material would be for these iterations of our devices. And now we can show off some of the actual parts we've made. Right here, I don't know if you can like recognize from like the model, but this one on the bottom left is the piece that's going to attach to our hollow needle. This piece next to it is the actual CO2 cartridge, not the actual one, but a little bit of a simulated model for the use of designing. And next to it is what's going to actually hold the CO2 cartridge in place. And then on the very right is the piece that actually connects down into the epinephrine cartridge and the CO2 flows through. And then this big one on the top here is what some of our designs have been to see like how we could integrate this into like a keychain model and have the device be compact and have an ergonomic design to allow for like good gripping and things like that. And that's why you see this like divot down here and the hand, the finger placements right there.
Awesome. And so some of our current challenges are that our mechanism is still entirely theoretical in nature. And of course, we're working on this currently by going through the 3D printing process. However, even during the 3D printing process, we've seen print failures and many discrepancies in our design that show areas of conflict and conflict of the mechanism actually working. So it just kind of emphasizes how important testing is, which has been an area that has been impacted a bit by the situation. However, we're still, doing our best to try and find ways to test these. And we're also seeing that the manufacturability of the nozzle will be challenging because of how intricate its geometries are. The diameter of the nozzle will have to be currently will be around 0.1 millimeters. So obviously that's pretty small. It's like it's very small is all I can think of. And we'll also, our ball mechanism will need to be constrained very tightly with tight tolerances in order to make sure that there's limited wear and tear on the mechanism inside. Because these balls are the main barrier for the device actuating, if there's any variability in the printing or the placement of the balls, then the balls might be able to slip out and the mechanism would be activated without intent. And at that point, then we would have issues with reliability of our build. So in the manufacturing of our device, we'll need to make sure to hold tight tolerances in order to make sure that we can constrain this ball in all directions and ensure that it won't be able to move out without intent. And we're also still having issues determining the exact distance between the needle and the cartridge to achieve the optimal puncture distance, because the current springs we have are theoretically optimal for this application with the optimal puncturing force. However, theoretical is theoretical, and only through testing will we be able to really fully determine this distance between the needle and the cartridge. And you know, with the 3D printing process, we're able to kind of take steps towards that. However, still something we're working on, and I do believe that with this printing process, we'll be able to get a little closer to this. And next, we have some plans for spring quarter.
So one of the most obvious things that we want to do in the spring quarter is actually get this 3D printed model put together and be able to say that we have like a final iteration for this year. And to validate our model, we really want to be able to put out a JDR, which is an R&D justification, and that will be able to, in that we'll be able to talk about every single aspect of our model separately and validate the usefulness and the ability for it to work in a repeated setting. The other aspect that we would need to do after we get this model validated would be to start testing on a bovine skin sample. So we would do this like in a lab setting. So something that maybe we would write up for this year and then actually be able to perform in person next year. And then another great way we can further the validation of this model is to start contacting physicians, getting them in contact with the device, have real life world application opinions on the efficacy of this device is a really important aspect of any medical device. So we want to get that done as soon as possible.
Awesome. And that does it for the projects we have right now. So I'll go ahead and do that.